Hey everybody, it's Mr. Carr again. Today we're gonna be looking at 4 day one. What we're getting into now is gonna be about graphing our trigonomic functions. A big part of the graph of this has to do with the fact that with our sine and cosine, they are periodic functions. So we're gonna get a repeating pattern. Okay. So it's so we're going to use, and then we're also, well, not today, but we're going to also be able to use our sinusoidal functions to help solve problems given a certain scenario. Okay, so let's start with talking about, zoom out a little bit here. These are the basic sine and cosine functions. These are basically our parent functions here. Okay, so when you look at them, we have a variety of characteristics there. Domain and range are consistent throughout them. We have a y-intercept here at 0 and y-intercept here at 1. We have x-intercepts that are repeated. We get a bunch of them actually. So if you actually graph both of these, which I'm going to do right now, I'm going to graph sine and cosine. They're actually pretty much the same curve, but cosine looks like it's just shifted over a little bit. Okay. They are continuously graphs all throughout the entire domain. Sine function has origin symmetry. So remember with origin symmetry, like this, if I kind of like spin it around, I can make that copy over there. Whereas cosine function has y-axis symmetry. So every point that's on the right side is going to be the same point on the left side here. Okay. In a basic sine cosine function, our maximums and minimums are at 1 and -1. Okay. Kind of ties it back to our unit circle as well. There's a relation to that on that part. Okay. As far as end behaviors go, these do not exist. Okay. There is no true end behavior because we're not approaching any specific value or we're not approaching infinity or negative infinity. This graph is going to go up and down the whole time because of this oscillation idea. So because of the oscillation, we don't really have a good way to describe our end behaviors here. Okay. So like I said, like the basic sine cosine function, let's go to Desmos real quick here. These are the two functions together. Okay, so you can see how the green function is just like a little bit shifted over here. We look at some key points, I should say. So we turn off the cosine for a second. So I like to look at this. This is our what's called a period. It goes from right here, it's one complete cycle. So you notice how it goes from 0 to 2 pi, just like my unit circle goes from 0 to 2 pi. Halfway through is pi. That gives me my first x-intercept after 0, 0. Okay. And then in between 0 and pi is pi over 2. So again, think about what the unit circle looks like. This is the top of the unit circle. So that means the sine of pi over 2 is 1. Okay. The sine of 3 pi over 2 is -1. That's the bottom of our unit circle. These are my 5 key points that can graph one complete cycle or one complete period of this graph. Cosine is going to follow a similar pattern here. But if I look at those similar 5 points, it looks like this then. Things are shifted. So instead of starting at 0, 0, we start at 0, 1. Then we pass through and have an x-intercept at pi over 2, 0. Then we go down to the minimum. So it's pi -1, 3 pi over 2, 0, and then 2 pi is 1. That's my complete, goes down and then back up and finishes up in the same position here. So when we look at these graphs, we can make some adjustments to them. They're going to be, one example is talking about the amplitude. So the amplitude of a sinusoidal function is half the distance between the maximum and minimum, okay, or half the height of the wave. So we have like this center line here, and we can go up in amplitude or down in amplitude. It does the same thing. So with our basic parent function, a was just equal to 1. Now we should also say this, we should do the absolute value of a because I can do a reflection with it if I do make it negative, which we'll see later. So that means amplitude is equal to the absolute value of a. A is showing up in front of sine and in front of cosine in these two formats. Okay, the next value we'll talk about here is this b value. The b value is what creates our period. Okay, so again, a period is going to be the same corresponding positions after a complete cycle. So you can see this graph right here, it goes down, it comes up, and then it finishes right here. These are the same positions on their graphs. Okay, we can always find the length of that period by taking 2 pi divided by the absolute value of b. And again, because if it's a negative, it can cause some reflections. So we want to do the absolute value of b to figure out how long is it, like how far apart is one complete cycle here. So that's going to help us with our grading, graphing purposes. This is another way of kind of looking at these two. So when we look at, we're going to talk a lot about A, B, C, and D as we go through this process here. But we can also kind of rewrite this middle section here as b times x minus h. Well, now think about this. Where have you seen h and k in the past? It's going to have a similar job here, just like we've done with quadratics or even exponentials, square root functions, things like that. Okay, so h and k is going to be this result here of factoring out this b out of this. Okay, so that will come back to later, but for today, we're just focusing on a and b and how those will affect the graph. So let's start with this one. Describe how the graphs of f of x equals sine of x and g of x equals 2.5 sine of x are related. Then find the amplitude of g of x and sketch two periods of both functions. So to start, we notice that a here is equal to 2.5. And that's the only thing I'm going to have. So I can describe that as it's a vertical stretch by a factor of 2.5. So everything's going to just stretch up. That's what a does, just like we way back in all of our other functions where we talked about the a value, which means my amplitude is 2.5. That's what all it is here. So I'm going to go ahead and draw this out. Okay. I like to start with just doing my 5 key points to start my sine function. The f of x function was sine. Remember when I did that one? We did 1, 2, 3, 4, 5. Okay, like that go up to +1 and -1 here. So it crossed here and it crossed here. This was 2 pi, this is pi, this is pi over 2, and then this is 3 pi over 2. Maximum, and then a minimum here. This is f of x. Okay, so those are my 5 key points. With my g of x function, because of the amplitude of 2.5, from this starting point, it's actually going to go up 1, 2, we'll go right here to 2.5. Same thing going down, -1, -2, make it a little bit longer, and this will be the 2.5 mark. All of the points are going to be the same in terms of their intercepts. So I'm actually going to still start at 0, 0 here. I'm actually going to still cross here and here. What the amplitude will do is it's going to take this point right here and stretch it up to this point. This one will stretch down to a -2.5. So we get this vertical stretch with g of x function here. Okay, and so let's take a look at how that looks on Desmos. So here's my sine function. And when I do 2.5, it just does a stretch. Okay, so again, now these key characteristics, instead of pi over 2 at going up to 1, it goes up to 2.5. Down here, it still crosses over the same there. Okay, so if I want to do another period, because it does say to do 2 periods of this, and I did not give myself enough space, so I'm going to have to shift some stuff over a bit. Okay, so if I want to do, let's go right about here, I might be able to do it with that. Okay, so I'm going to extend that out a bit. So I'm going to do another 5 key points. So if it's 2 pi here, so I can go 1, 2, 3, 4, 5. I know that the graph is going to cross here and here. Oops, minimum. Wait, 2 pi. Yeah, let me just do this. So it's going to cross at 2 pi. Then the next one here is going to be, we're going to add a pi over 2 to that. So that's 4 pi over 2. So this will be 5 pi over 2. This will be 3 pi. This will be 6 pi, or that's 6 pi over 2. This will be 7 pi over 2, and then 4 pi here. So it's going to end in this spot. So they'll be here and here. Here's my second period there. So for the other function, to complete that, again, this is going to go up higher, and this is going to go lower. So it's going to go here, cross at the same point, and then complete that spot there. Okay, so there's my 2 complete periods of both of these functions. Let's take a look at cosine versus -2 cosine of x. Okay, so again, the a being a -2 is going to do 2 jobs for me. The first job is the fact that the absolute value of -2 equals 2 tells me that it's going to have a vertical stretch by a factor of 2. Okay, so we're going to see that stretch again. But being negative, since a is negative, the other thing it's going to do is it's going to reflect over the x-axis. Okay, so this is my prediction of how everything should look. We're gonna do, okay, good, just one period this time. Got a little bit more space to work with there. Okay, so my first cosine function, remember, I'm gonna start up here. So I'm still gonna go 1, 2, 3, 4, 5. So I can go, it'll cross here, it'll be a minimum here. I made those too high. Let me make the point a little bit lower here. This will be 1, this will be 2, this will be -1, and this will be -2. So I'm going to cross here, there, cross there, minimum, cross, and back to the maximum. So here is my cosine function. So that's f of x. G of x, as we said, is going to do two things to it. So first thing is it's going to stretch. So when I see that, I would take it up to here normally with a +2. But then being a -2, it's going to reflect down here. So my first point is actually going to start down here. The stretching does not affect the x-intercept, so I'm still going to cross here. Then I'm going to go up to the +2, cross here, and then back down here to -2. So here's my reflected and stretched cosine function. Okay, and again, just to compare, so if I did cosine here, here's my -2. It is reflected and stretched. Okay. Now, another thing that can be affected is the length of that period. As we mentioned before, the b value is what determines that. So in this case, I'm going to use f of x equals a times the cosine of bx here. Now, in this case, b is 1, so that's a normal period. Okay. This case, we have the cosine of x over 8, or another way of thinking of that, and put it in blue. G of x equals the cosine of 1/8 x. Okay, so now my b value is 1/8. Remember, we found the b value is related to the period because we could take, or sorry, wrong way. The period length is equal to 2 pi divided by the b, or the absolute value of b. So in this case, I'm going to take 2 pi divided by 1/8 here. Well, if I'm dividing by that fraction, that's the same as multiplying by its reciprocal. So it's going to be 16 pi. So this one is going to be a little bit weird. When I graph this, 16 pi is one complete cycle. So if I draw this out, draw as best I can here, I'm going to start with, I'm going to make it nice and long here. I'm going to start with my g of x. Okay, so I have no amplitude beside, or I have my amplitude is 1, so I'll take it down to a -1. Okay, so I'm going to spread this out. So 1, 2, 3, 4. This curve is going to 16 pi. The halfway mark is going to be 8 pi. Halfway between 8 and 0 over here is going to give me 4 pi. And then this will give me 12 pi right here. Cosine function starts up here. Then it's going to cross. It's going to hit the minimum. It's going to cross again. It's going to hit the maximum. Really close enough. There's my cosine, my g of x function here. My parent function I'm going to put on here as well. But remember, the normal cosine function completes a period in only 2 pi. 2 pi is going to be right here. Well, this is going to be weird. It's going to complete one full cycle up until that point. It's actually going to go down. So I'll put the halfway here, halfway here. There we go. It's going to cross. It's going to come down. It's going to cross. Come here. There's f of x. So what's happening is we are kind of getting this horizontal stretch. So I can describe it as having a horizontal stretch, or the period is 16 pi, so it's much longer. And again, let's take a look how Desmos tells us that. Here's cosine, and there is the cosine of x over 8. You can see it takes all the way over here. There it is, 16 pi to complete that cycle. Okay. So one last example to talk about, and that's with frequency. Frequency is telling us how many number of cycles are completed in a given amount of 1 unit interval of time. So frequency is always going to relate to 1 divided by period here, which means we can also take it as b divided by 2 pi will tell us our frequency. Okay, so how does that work for a word problem like this? A bass tuba can hit a note with a frequency of 50 cycles per second, which is the same as 50 hertz, and an amplitude of 0.75. Write an equation for a cosine function that can be used to model the initial behavior of the sound wave associated with the note. We're going to use this general format, y equals a times cosine of bt. A is the amplitude, that's my 0.75. That one's straightforward. But the B value is going to have to relate to the frequency. So since the frequency is 50 cycles per second, the period is 1 over that. It's 1 over 50. So I need to use that to find my B value. So just like my period is equal to 2 pi divided by B, my B value is going to be 2 pi divided by the period, which in this case is going to be 2 pi divided by 1 over 50. So if I multiply it, turn that into a multiplication problem, my B value is going to be 100 pi. So I have my B value, I have my A value, my whole equation is 0.75 times the cosine of 100 pi t. That's the equation that models this. We're not going to graph it in this case, but that is my final part. And that's it for our basics. We'll talk more about the graphing of this in a future video, but that's it for today. Take care, everybody.